Okay, I'm going to record a quick overview of exam 23 if you have like 10 you're trying to cram, or exam string 24, and you want to just know what concepts might be on the exam. This is target audience here. This is kind of just a tricky conceptual question. It's saying, a capacitor, it'll absorb the current, and so long after a switch is closed, there won't be any current flowing through this wire. And so when you're assigning voltages, you can effectively just treat it as two resistors in parallel. And so this will get 3 volts, and this will get 3 volts. But even though there's no current being put here, and so that changes how the volts are assigned, the volts here are still obviously distributed to the volts here. So there's still 3 volts coming in through here. Multiply with this equation, you get what you need. This is just a drawing out. Hold on, it's like this, just drawing out the diagrams, reducing to what you need. You should hopefully be familiar with that at this point. This is the same thing. This is just reducing the diagrams, the resistance diagrams. This is like the junction rules, multiple EMFs. When you see that, that's what you need. Use the junction rules. I2 is equal to I1. And then find loops which are included in those junction rules, and find kind of common ground. Eliminate a variable, so you only get one variable. Here they actually give you saying this I3 was actually 0 volts. Which just kind of streamlined everything, but should be familiar with how to solve those systems of equations. Here, this is probably a question that will as well. If a magnetic field and electric field are equal, what's the magnitude of a field and how do you orient it? Sometimes it will ask, find the electric field, sometimes it will find the magnetic field. The calculation is pretty simple. Sure, you're familiar with checking where the force of each field is going and how you need to orient each field to oppose each other. Note that electric field, it will travel, a negative particle will travel in the opposite direction of the field, positive in the direction of the field. And then with the B field, you can use the right-hand rule, right? Take the velocity, go in the direction of the B field, and then if it's pointing, wherever it's pointing, that's where a positive thing will go. Otherwise, flip, that's where a negative thing will go. Negative particle. Here, you're using this formula up, down, here, essentially just relating velocity to radius for a certain b, so you can solve for the b. Also, given a velocity, if the b is coming into the page, this is a positive, it will be forced to the left, so you need to realize that it's going out of the page, and that's forcing it to the right. Here, I feel like there's definitely going to be a conceptual question on this, if everything holds up. So here, if you curl your fingers around the direction of a current, your thumb will indicate where the magnetic moment is facing, and the magnetic moment will always orient with the B field, parallel to the B field. That's what the torque is. Here it is already oriented with the B field, so there is no torque. If it was, say, facing downward and the B field was here, it would move counterclockwise in order to, move itself in line with. But here it's already in line. There's nothing to worry about. This is, a simple get the force on each side of the square problem. This force varied based on x, so, the top and bottom of the square canceled, but one of the vertical sides had less force than the other. Find both, find the difference, find which way it moves, and you're done. This one also a problem we've seen before. It's kind of like this, where you have one force in a circle going in one direction. Instead of using this, which you do for the wires, or this, which you do for the wires, you use this for the circle. And you essentially just solve for one circle using this equation. solve for the other circle, subtract them, and then realize that like this one is stronger, and since this current is heading this way, you're going to be getting something out of the page. Here, this is literally just looking at every single one, right-hand ruling for the direction, right? These two are counterclockwise, these two are clockwise, and then seeing that all the right, which means that in the center, you have this magnetic field going to the right. Here, this is like this wire question on the homework, where you use this equation here to individually determine every little thing onto a single thing, a single wire, and I guess it's more so this equation. And then you just add them up, see what the net force is. Here it was 0. This is a literally like said solve for that integral. So you just solved for the I enclosed, which was just half of what they gave you, multiplied by mu naught. What was interesting here is that you always have to check the direction of the path, right? The path here, since it's like so, your thumb points into the paper, which means that it's kind of like it's opposed to the current that it's being given, which means that you have to use apply a minus sign here. This is a standard conceptual like flux question. Here you have increasing magnetic field out of the board. Here it's increasing into the board. So obviously the loops make field or make current to counter that. B previously was going too much, or there's increased amount. So it tries to go out of the board. It does that with a counterclockwise rotation. A does the opposite. This is an annoying question. Basically, it's about a flux that varies sinusoidally. Also, a coil, so you have to multiply everything by 50, all the flux and all the EMF. But it's a coil that with a B field that varies sinusoidally due to a rotation. So the important if you ever have this and you need to differentiate into your EMF, that this omega inside the sign comes out, and you're able to use that for calculations. If you're ever using an omega, sure you know if you have rotations a second, which is usually when they give you hertz, multiply by 2 pi to get radians a second. That's what omega is. And sometimes they'll give you the t, the seconds per rotation. Here, the period. Then you will have to like flip to get rotations a second, and then multiply by 2 pi to get your omega. This was a cool one. So it was a but the B field, it was changing over time, but it was actually a wire, so you had to use this formula to solve for the B field, and they give you the change in current. I'd say if you can do both problems individually, you'll be able to do this. It's nothing too difficult. It's just kind of plugging stuff in until you get what works. This is a really easy problem. L, right after a switch is closed, L acts like a dead wire. 2 resistors, and yeah, free problem. Here, the energy stored in an inductor. This is just using for an LC circuit here to determine the amount of current running through over time with an initial charge, which you can see it's just this, and then using that current to solve for the energy stored in an inductor. And then this one here, this is an RLC circuit. You are this formula here, given a certain time and everything. So you're given a big Q. You do have to solve for how long it takes for 10 complete cycles to pass, which, solving 1/√LC LC for omega. This is something you can do in these types of circuits. If you have an L and a C, instead of having it given to you, you can solve for it. And then since that's the amount of actually divide by 2 by the cycles to second flip for seconds per cycle, multiply by how many cycles you need to get T. And then, yeah, you're just solving that. Make sure you're comfortable with using ln's on your calculator. Your phase angle, it's just using this formula. Make sure you're comfortable with, if it says EMF source, it doesn't necessarily mean volts. Check the units. If it's hertz, that's the rotations a second, which you can use to omega. And then finally, the resonance question. So here you want to maximize amplitude of the current. This is also, you can said before, is maximizing power, but do that by setting this equal to 0, which you can solve and you get you get an answer. And again, multiply by 2 pi your hertz to get your omega. All right. Again, if you haven't seen the other one, just good luck. You're prepping, so we'll see what happens. Good night, everyone.